Okay, let's take a look at this example problem. Like I said, we got 200 kips of force pushing down on this column. Column sits on a footing. You want to use the direct stress formula to calculate the stress in the column and then the stress under the footing. 200 kip load is pushing down, so therefore my column's in compression, so it's a compressive stress. We're considering this a short column. The footing, like I said, is probably sitting on some soil. So the stress that's caused by one thing sitting on top of another thing is actually called a bearing stress. Both of those are direct stress, applications of direct stress. So they are both controlled by, again, the formula that we talked about. Stress is equal to force divided by area. You got to think about the area as what is the area resisting that load. So, in the column, you're going to tell me that that's 200 kips. The area that's resisting it is 1 square foot, because again, you're looking at the cross-sectional area of the column here. Okay, so that's 1 by 1. That's 1 square foot. So the stress is 200 kips per square foot. KSF. Now, is that a lot? Well, it depends. I don't know. What material we're talking about? I mean, we really didn't say what material we were talking about. This could be concrete, could be wood, could be steel, could be aluminum. I mean, that's going to differ in all those cases. It would differ if this was a short column, which I said it was, and a very long column. I mean, is that stress going to be too much? I don't know. We'll have to, that's what you get into as you start getting into the design. What about the stress under the footing? Well, again, stress is equal to force over area. The force is what? The force is 200 kips. Now again, if you were really getting into this, you'd say, well, then there's the weight of the column, and then the weight of the footing, and so on and so forth. But we didn't say anything about weight, so we'll just neglect those. So we'll say 200 kips again. What's the area? 5 by 6. It's that rectangular cross section. In bearing, it's the actual cross section of whatever it is. In this case, the footing that's bearing on the lower strata, which might be soil or whatever it is. So in this case, that's 30 square feet, 5 by 6. What's 200 divided by 30? 6.67, again, in units, kips per square foot. Is that a big pressure? Huh?
Not as big.
Not as big, that's right. The answer is you don't know. I mean, it depends on what's supporting that. If this is soil, if this is like clay, well, 6.67 kips per square foot's pretty big. If this is, limestone or something, limestone will be able to handle 6.67 kips per square foot. So again, I mean, right now we're just getting the mechanics of the calculations down. When you start getting into actual design, then you start, hey, this is big, this is not so big, and so on and so forth. How many square inches are in a square foot? 144. Okay? So if I asked you, hey, convert 200 kips per square foot into kips per square inch, what would you do? You divide this by 144. So divided by 144, square inches per square foot, square feet go away, and you'd get 1.39. The units would be KSI, kips per square inch. All right? So again, I just always like to point that out because, you might see 200 kips per square foot and you're thinking, man, that's, wow, that's a lot. You start looking at kips per square inch, and now it's not such a big deal. A lot of our materials, when you get into them, they'll be met, when you look into like the codes or the manufacturer's literature, I mean, they'll talk about things in kips per square inch or pounds per square inch. So if this is, you said 1.39 kips per square inch.
Yeah.
If this was steel, or if this even was concrete, that's not that much. I mean, steel, it's hardly anything. Concrete, it's, most of our concrete, we'd say, is 4,000 pounds per square inch, or 4 kips per square inch, okay, under compressive stresses. All right? So, you get sort of the concept there.